We'll continue with our aerodynamics topics. In the previous videos, we had talked about equations along a stream tube. Then we talked about streamlines, streak lines, path lines. Then we talked about vorticity and rotational flow and irrotational flow. We also developed a governing equation for conservation of mass. So we're going to continue with that. Again, as is our practice, we will do it in 2D, derive it rigorously in 2 dimensions, but then we will extend it to 3 dimensions. When we are deriving it here, we are going to go ahead and do it for viscous flow. Although viscous flow is not the primary focus of this course, that's because we would need to talk a little bit about boundary layers, viscous drag later on. So knowing where they come from would be very helpful. There's a companion course at Georgia Tech called AE 6009 graduate course where the viscous flow topics are covered in greater detail. But we are going to go ahead and derive the equations here. So let's get started. I'm going to go to a full screen view so that we could we're going to go to the full screen view. All right. So why would anybody want to know viscous flow, especially aerodynamicists? Well, if you're going to design an aircraft or an airfoil or a wing, you're not only worried about lift and pitching moment, but you're also worried about the drag. You can't get very far computing the drag of an aircraft unless you know something about viscous flow, whether you're designing an aircraft or analyzing an aircraft given configuration. Same goes for other components such as the compressors, turbine blades, turbofans, helicopter rotors, propellers, wind turbine, you name it. If you happen to work in the automotive industry designing an aircraft, car, then you need to know something about the drag, viscous characteristics. So you could talk about flow separation, pressure drag, skin friction drag, and so forth. Same thing with ships, and also even the sails, that are used. They are nothing more than very, very thin airfoils, if you will. So they have certain characteristics of lift and pitching moment, but they also have drag. So they could have flow separation taking place at certain parts on the sail. And so we need to know these type of concepts in order to be a good aerodynamicist. So that's our objective. It's also important in the internal flows. If you're analyzing flow through a channel or a duct or a pipe, remember molecular viscosity can transport not only the momentum, which is velocity, but it could also transport heat, molecular diffusion of heat. It could also transport chemicals. For example, molecular diffusion of species from one part of the flow to the other. Same a turbulent mixing flow not only can exchange momentum, but also mass and heat. So this design of these devices, you may be asked to compute a cooling fan for an aircraft or a heater for a probe that is exposed, a pitot probe measuring the velocity, or may be asked to heat a leading edge of an aircraft to prevent icing. If you don't know what type of heat transfer is taking place from the outer flow to the solid surface and vice versa, we cannot do a good job. Similarly, in biomedical applications, whether you're talking about flow through arteries and veins, for air or blood or other liquids, or designing bio devices such as heart pumps or open and close valves, it's important to be able to capture these physics, model them, so that you can understand what's going on. So as I mentioned to you earlier, not only mass transport, momentum transport, but also mass transport in chemically reacting flow. It depends on viscous phenomena, molecular diffusion, and turbulent eddy diffusion. We would use a variety of units depending on where you are on the Atlantic. In the United States, we often use British system of units, but nearly all the rest of the world, including the British, use the international system of units. So you just need to be conversant with both systems of units, because we do not know where we would be asked to work, which country, which partner we are going to be working with. So you may have a United States team partnering with a Japanese team on a aircraft design, for example. Then you need to know both systems of units, be conversant with it, so that you are able to talk to each other in their language. We have already talked about concept of continuum. Air is made of molecules, discrete molecules. We no longer treat them as individual particles because they have individual velocities, individual kinetic energy, and so forth. But because they bump into their neighbor, one particle cannot be streaking through the space without ever coming into contact with their neighbor because of the close packing. Therefore, some averaging takes place. So it's like a Peachtree race. At the start of a race, one person cannot run very, very fast because he or she will bump into their neighbor. So the whole group is moving as a collection of group of people. Only towards the end line, then the separation takes place and one person is streaking past the other one. So mean free path we mentioned is the distance between the collision, two molecules before collision occurs. Knudsen number takes the ratio of this mean free path to the vehicle dimension, whether it's an airfoil chord, or the wing root chord, or wingspan, or a fuselage length, doesn't matter. So the ratio, if the ratio is very, very small, then concept of continuum applies. If the ratio is very, very high, or of the order of 1, then concept of continuum breaks down. The textbook by Anderson, which I have mentioned to you, we are not requiring in our course material, but if you happen to have it in the first chapter, they discuss these concepts in greater detail. We had already talked about density, velocity, and temperature. So we are going to start developing the equations. We already developed the conservation of mass in 2D in the previous video, but now we are going to also look at the conservation of momentum. So remember the other properties of pressure. Pressure is a normal force per unit area, Newton per meter squared, or pound force per square feet. Normally, it's always normal to a surface, whether it's an airplane surface or imaginary control volume boundaries. Sometimes we use the term gauge pressure. Is the static pressure P from which we subtract the atmospheric pressure. For example, when you measure the pressure inside your car tire or a bicycle tire, you may say it's 30 psi. It's really 30 psi over and above the atmospheric pressure. Okay, that's the gauge pressure. So many pressure gauges measure the difference between the actual pressure and the atmospheric pressure. Therefore, gauge pressure can be negative or positive, whereas the static pressure P is always positive. Now we have to introduce another property of the fluid called viscosity. This comes from Newton's earliest work. Remember, Newton was born in the 17th century. He has contributed a great deal to solid mechanics, astronomy, universal gravitational law, and so forth. Not surprisingly, he also contributed to fluid mechanics because he was very interested in the fluid resistance. So in this hypothetical experiment, he took two plates of area A separated by a small distance h. The bottom plate is held fixed. The top plate is moving from left to right, V. Then he found that certain resistance occurs, so he needed to exert a force on the top plate to move it. Otherwise, it would not move quite so easily. So if you take the force divided by the area, you get a tangential stress, which you call a shear stress tau. It's got the units of Newton per meter squared. He found that Newton per meter squared is proportional to velocity. If you pull it very fast, you need more force. Slowly, you need less force. Surprisingly, inversely proportional to the distance h. If the h is small, if the two plates are close to each other, it takes a lot of force. So the h went to the denominator. Then he found the proportionality concept was a constant, regardless of v or regardless of h, that constant was mu. So he called that the viscosity. This is the property of the fluid. That means different fluids will have different viscosity. Oil will have one, water, air, blood, liquid metals. They all have different viscosity. So it's a property of the fluid. Property of a fluid means you can look it up in an almanac or in an encyclopedia. It turns out viscosity is a function of temperature, both for gases and liquids. Air is a viscous fluid, sticky. Most other fluids are also viscous. So when a fluid moves past a stationary surface, you exert a tangential force. So in the case of a boundary layer over an airfoil or an aircraft, this is the aircraft surface, which is the bottom plate. The top plate is not really a plate, it's a velocity moving from left to right. In between the two, you get a velocity gradient, which we call a boundary layer profile. So the boundary layer profile has got a velocity gradient, velocity over distance at the bottom wall, multiplied by viscosity is the shear stress. Okay. So Newton found that this shear stress is proportional to viscosity. As we mentioned to you, this is a property of the fluid, not a flow. That means we can look it up. But you do need to know something about temperature in order to compute the viscosity. Why? In liquid, what happens is viscosity is caused by the intermolecular forces. If you have two molecules separated by small distance, then the electron cloud over one molecule is attracted by the proton, which is in the core of the second molecule, and vice versa. Therefore, if you move one molecule from left to right, this attractive force causes the other molecule to tag along. So there's a force that is generated in order to separate them from each other. This force is the viscous force. So in liquid, it's caused by intermolecular force. So when you heat a liquid, molecules expand, then the attractive force decreases, therefore viscosity also decreases. That's why if you heat either a syrup, pancake syrup, or an oil or a greasy fluid, then the viscosity actually decreases with temperature. In the case of gases, we don't have molecules quite so packed. So they are moving, they collide with each other, so they produce pressure, but they also move and cross one boundary to the other like a control volume. Then through the random motion, they are bringing in the molecule. For example, this room has got several windows. So if randomly a molecule comes in and randomly a molecule moves out, mass may have been conserved because one molecule came in, other one moved out, but one of them may have brought a higher velocity than the other one. Therefore, it may have increased the momentum without collision, without existing any force. So the random molecular motion causes the viscosity, not just collision. Collision is usually associated with the pressure. So when you increase the temperature in gases, this random motion increases, this random velocity component increases, the momentum transport attributable to the random motion increases. Therefore, the viscosity increases with temperature. There's a law called Sutherland's law, which you could look up in Wikipedia that discusses how to compute the viscosity for various fluids. So now we are going to develop governing equations. These were developed soon after the concept of viscosity was coined by Newton in the 17th century. So these things took place towards the end of the 19th century, beginning of the 20th century. Okay, almost 100 years later, after Newton. So we are going to do it for 2D because it's very easy. We are going to do it for unsteady flow. We will initially keep the density as a variable. Then sometimes I will drop the density. Then when the density is brought out of a derivative or disappears completely, then you know it's a constant that got cancelled everywhere. Then that means that particular form is called incompressible. So the equations we are going to develop here and also their 3D counterpart are called the Navier Stokes equations. They were developed by Navier in 1831 and then more rigorously by Stokes in 1845. So they really in the 19th century they developed it. Now we are in 2021, so it's going to be almost not 168 years later. You know, my age is showing. It's more like 176 years later. These equations are still standing with no modifications whatsoever. To understand how this viscosity produces viscous stress, we need to take a step back and look at solids, which we know something about from elasticity. We know from our basic solid mechanics that if you take a one-dimensional material of length L, and if you pull it, its new length is delta L, extra length is delta L, then the delta L, which is the extension, divided by the original length L, is called the strain, which is a non-dimensional number. It needs a certain force. Force per cross-sectional area is stress. So if you think of it as a rod-like substance, the rod cross-section is area, force over area is stress. If you divide the stress by the strain, you're going to get Young's modulus. So stress is linearly proportional to strain. So if you want more strain, more deformation, you have to increase the force. So more the force, more the strain, less the force, less the strain. But if you do this to liquid, remember liquid is like a jello-like substance. If you try to pull it, it'll just come apart, right? So you are not going to have a finite strain, you're going to have an infinite strain. Likewise, if you take a fluid, apply tangentially force or a tangential stress, it'll deform, continue to deform in the tangential direction forever. So we cannot say stress is proportional to strain. We need to say stress is proportional to the rate of strain. That means it's not distance over distance, it's velocity over distance, like Newton had seen here. So velocity over distance. So we are talking about a velocity gradient rather than a displacement gradient. So we will use the elasticity equations that were developed earlier. Then we are going to generalize it. Wherever we have a displacement in the x, y, or z direction, we are going to replace the x, y, or z with a velocity in the x, y, or z. Wherever they had a Young's modulus, we are going to replace it by viscosity. So more or less, this is the approach that Stokes, the Englishman, developed in 1845. All right. So stress is proportional to strain in the elasticity. But now we are talking about not strain, not a distance over distance, but velocity over distance. So we are talking about the time derivative of strain or strain rate. So when you apply a tangential force, it will continue to deform if you have a filled with liquid. So you're not going to stop after a while. On the other hand, if this is a piece of rubber material, if you apply a stress, it will deform only a finite amount, then it will stop. So a definition of a fluid is its ability to continue to deform when you supply a tangential stress to it. Okay. So Hooke's law does not work, elasticity does not work, so we'll have to generalize it. So we are going to use a rate of strain or strain rate, velocity over distance, rather than the distance over distance. So this is what Newton did. This is what Stokes also generalized it. Newton did it to a single dimension, just a very simple problem that he visualized it. Stokes generalized it to multiple dimensions. So he took the elasticity, stress versus strain law in 3 dimensions. So wherever there was a strain, he replaced it with strain rate. These cannot be proved at all. They can only be verified in practice. So what did he do? What type of relations he developed? He said, okay, before I define the stress, I need to know is it a scalar, defined only by a magnitude, or it a vector, defined by the magnitude and the direction in which it is acting, or is it a tensor, which requires additional information about the phase on which it is acting. So stress happens to be a tensor. It requires magnitude, requires direction, requires some information about the phase, whether it's a physical, rigid phase, solid phase, or a control volume boundary, which is a mythical fluid boundary on which we are exerting stresses. How does it go? Let's say this is a fluid element. So let's say this is your right side boundary. Tau is the stress, which has got a magnitude, which is Newton per meter squared. It's acting in the x direction. Is in the positive x direction. The first subscript is the phase. So in this case, the phase has got a unit normal vector pointing along the x direction. The force is also pointing in the same direction. Okay. So you would first draw the unit normal. If it is in the positive direction, then the stress would also be positive. Okay. I'm going to show you some examples where the opposite occurs. So about the left side, now the unit normal vector is pointing in a negative direction. Therefore, tau x-axis will be pointing in a negative direction. So magnitude, the first subscript talks about the phase. The second subscript points to the direction in which the stress times the area, which is the force, is acting. How about the top boundary and bottom boundary? Let's say the side boundary, shear stress. Again, you got a units of tau, Newton per meter squared. Is acting on the phase x. Because its unit normal vector is pointing the positive x direction, this shear stress, even though it's pointing in the y direction, it will be pointing in the positive y direction. So this is the convention that we will use on this phase. How about the left phase? Because now the unit normal vector is pointing in the negative x direction, this stress is pointing in the negative y direction. So this is the direction in which the stress times the area is pointing, which is a force. This is represents the phase. Tau represents the magnitude. Okay. So you could do that for any phase. So you would get tau yy, tau yy, tau yx, tau yx. We have already seen these two components. So you could do it for 3 dimensions. For a 3-dimensional Rubik's Cube like control volume, you could define the tau acting on all the directions. Okay. So first thing that Stokes realized was that stress is a tensor. Then he said conservation of angular momentum. Think of this control volume. Think of it as a piece of fluid. So tau yx is here is acting in a clockwise direction. Tau x is clockwise direction. So this is going to produce a clockwise moment. Okay. Tau xy and tau xy is going to produce a counterclockwise moment. You have to do more than just stress. You have to multiply by the area times the distance. So I'm just giving you the way in which he did it. But if the clockwise moment need to balance the counterclockwise moment, then it can be mathematically shown even in steady flow or unsteady flow that tau xy should equal tau yx. Okay? So even though they have different significance as well as the subscript and y, in terms of magnitude, tau xy equals tau yx. This is true of solid mechanics, which you may have seen in your high school or in your college statics or elasticity courses, and it's true also for fluid mechanics. Therefore, when Stokes did a tau xy, the same definition holds for tau yx and vice versa. Remember, Newton had only mu times dv du dy, because he only had two plates, one moving at a velocity u, other one was separated from the other plate by a distance y. But now he generalized it with the other deformations. Where did he get all these terms? These came from elasticity, solid mechanics. So wherever he had a distance by distance in elasticity, he replaced it by corresponding velocity over the distance. So this is for the shear stresses. Then in the normal direction, when y becomes equal to x, u will become equal to v, or v will become u. Then he got 2 mu du dx. Same way, 2 mu dv dy, 2 mu dw dz. So he got these three terms from expressions like these, okay, from elasticity. But he had to add an extra term, lambda times this quantity. We are going to review this. By the way, this is del dot velocity vector. You may remember in conservation of mass, del dot v is 0, we saw in our previous video. Therefore, this term goes away in incompressible flow, but in compressible flow, this has got some finite magnitude. Why did he have to add this extra term? Why did he have to bring up an extra lambda? What does lambda mean anyway? How do we relate it to mu? So he said that's because I had to reconcile whatever is happening in a fluid that is in motion with a fluid that is at rest. When fluid is at rest, we have hydrostatics. When a fluid is at motion, we have hydrodynamics. When a fluid is at rest, if we take a mythical control volume, it's got 6 faces like a Rubik's Cube. If we take the average of the pressure forces on all the 6 faces, remember pressure is force per unit area, Newton over meter squared. If we take the average, that's the average pressure of the fluid. Okay. By the way, if we have a bottom face is at a deeper depth than the top face, the bottom face may have a higher pressure P compared to the top face, pushing the fluid up, which is balanced by the weight of the fluid that is pushing it down. You know, the Archimedes principle, okay? The buoyancy force caused by the pressure difference is balanced by the weight. Okay? That's why the ships, they don't sink through the water because the buoyancy force balances the weight. In hydrodynamics, we want to preserve the same significance. Therefore, we say if the normal stresses on all the 6 faces are added up and divided by 6, I should get pressure. That means on the surface, you're going to have pressure stresses, but also viscous stresses. Then these stresses, when you add them up over all the 6 faces, they should add up to 0. So this is called the Stokes hypothesis. These 6 relations are called Stokes relations. So they are slightly different things. They are not the same. Okay. So this is a cube of fluid, whether it's at rest or motion. These are the pressure stresses acting on all the 6 faces. So in hydrostatics, the average pressure would be average of all these pressure stresses on the 6 faces. So he wanted to preserve this even when this is moving. But when the fluid is moving, in addition to the pressure forces and the pressure per unit area on the 6 faces, we also have the normal stresses which we talked about earlier. Okay? Tau xx is acting this way. Here, tau x is acting in the opposite direction. So he said I should add all of these things, then I should add them up to 0. So he said I'm going to add tau xx plus tau yy plus tau zz. I'm going to add them up to 0. So when he got that, he got 2 mu plus 3 lambda times du dx plus dv dy plus dw dz equal to 0. 2 mu equal to 3 lambda, therefore lambda equal to minus 2/3 mu. So this slide and this slide together are called the Stokes hypothesis, whereas this slide refers to Stokes relationships, stress versus strain rate. Armed with this knowledge, now we can develop the governing equations. We are going to deal with the Newtonian fluids because in Newtonian fluids, stress is linearly proportional to the velocity gradient. Remember, viscosity times some linear gradient of velocity. Lambda times some linear gradient. Viscosity times some linear gradient. Air is a Newtonian fluid. Water is a Newtonian fluid. So Newtonian fluids have a linear relationship between the stress and the strain rate. On the other hand, blood, liquid metal, and some other polymers, chemically produced polymers, they have a nonlinear relationship between the stress and the strain rate. So you have to develop those relationships and then apply them. Okay. So when you use a computational fluid dynamics solver such as Fluent, I hope we have some time to talk about it later on, perhaps in this course, when we are done with all the required material. We will show you can select Newtonian fluid or non-Newtonian fluid. Basically, it's picking up these relationships versus a corresponding relationship for blood, or for liquid mercury, or liquid paint, or a polymer, and that's what it's using. All right, so that's the Newtonian fluid versus non-Newtonian fluid. Most of the fluids people deal with in aerodynamics and hydrodynamics are Newtonian fluids. So we have already developed the control volume in our previous video. So we took a small control volume of height delta y, width delta x, surrounded by 4 faces. It's got a unit depth perpendicular to the plane of the paper. We looked at the rate of change of mass within the control volume. Then we said this change must have occurred if anything changes in the interior. Let's say the mass goes up, that means I'm bringing more fluid either to this boundary or less is leaving to the right boundary. More is coming into the third boundary or less is leaving to the fourth boundary. So we summed up all the 4 boundaries. Then we took divided it through by delta x, delta y. Then we took the limit as delta x and delta y go to 0. We got this relationship. This is our conservation of mass that we have previously developed. Now we are going to do the similar thing for conservation of momentum. So we will develop it for u direction, x component, or the u velocity, u momentum equation. Then we will talk about v momentum equation. So we already have some understanding of viscosity, viscous stresses. We don't need to worry about conductivity because we're not doing energy equation. So we only need to know viscosity and viscous stresses, which we have covered. So now let's look at the rate of change of momentum within the control volume, instead of rate of change of mass. Newton said the rate of change of momentum is caused by some forces. The forces may be happening on the boundaries or in the interior, some kind of a body forces. Or you could also be bringing in more momentum to the left boundary than the right boundary, bottom boundary than the top boundary. So you could also be convecting in, convection effect, bringing in the momentum from the exterior to the interior through the boundaries. So we take a control volume. Area volume is delta x times delta y times 1. The mass is rho times delta x times delta y times 1. U momentum is rho times delta x times delta y times 1 times u. So you can bring the constant quantity outside, delta x times delta y times 1. That's meter cubed. But you keep the variables inside. So the rate of change of mass is the time derivative of rho u multiplied by delta x times delta y times 1. This is caused by either convection effects. Look at this phase number 1. Area is delta y times 1. Mass flow rate is rho times u times delta y times 1. Momentum flux is rho u squared times delta y times 1. Mass flow rate times the u component of velocity. How about phase 2? The same thing, except the velocity is leaving, because this is the positive direction for u vector. So by convention, here the momentum is leaving, so I'm going to put a minus sign. How about the bottom boundary? This fluid is coming at a velocity v, so the mass flow rate is rho times v times area, which is delta x times 1, but it's bringing the u momentum. Therefore, rho uv delta x times 1 on phase 1. On the top phase, you are removing it. So we will sum all of these 4 up. Then we will divide it through by delta x times delta y times 1, like we did in the conservation of mass. How about the pressure forces? Here the P is acting from left to right, P times delta y times 1. Here P is acting in the opposite direction, slowing down the momentum, negative of P times delta y times 1. Tau xx here is pulling it. Tau xx times delta y times 1 is positive. Here tau xx is pulling it backwards, so it's minus tau xx times delta x delta y times 1 on phase number 1. We should not forget the shear stress. This is contributing to the increase in the momentum. This is tau yx times the area, which is delta x times 1. In this direction is positive, phase number 4. This should be phase number 4. This is phase number 3. So group them together again. Then divide through by delta x times delta y times 1. Then the limit as delta x delta y goes to 0. Then you get this equation. This is the u momentum equation. Rate of change of mass. The momentum term is here. Convection terms are here. Convection terms are here. I have brought the pressure terms to the left side because this is an inviscid, nothing to do with viscosity. This is the viscous terms right here. So this is Navier Stokes equations. If you neglect the viscous terms, then you get the Euler equations. Okay. So Euler equations are a subset of Navier Stokes equations. Long time ago, we developed the Euler equations along a stream tube for a stream tube. Now we have generalized it for a general 2D flow. So same way we can develop a V momentum equation very similarly. Then you will get a similar looking expression. As an exercise, I would like you to try to derive this to make sure you get this expression, please. So in summary, we have the conservation of mass, conservation of u momentum, conservation of v momentum. Let's count the number of unknowns. P, rho, u, v, 4 unknowns. Viscosity is known, it's a property of the fluid, function of the temperature. Now we have 4 unknowns. Here we have only 3 equations. So you need a 4th equation, which is the energy equation in compressible flow. But in an incompressible flow, rho does not change at all. Then these 3 equations are sufficient. We can solve them at least in 2 dimensions. We could do the same thing in 3 dimensions. We can continue in other ways. So I would like you to take an exercise in simplify. Plug in the Stokes relationships here for tau xx, tau xy. And assume incompressible flow, therefore rho equal to 0. Take advantage of the conservation of mass, du dx plus dv dy equal to 0. Then manipulate slightly and show that you can get this relationship. So this is left as an exercise for you to try it out. When you do that, this viscosity is called a molecular viscosity, which has got a units, something to do with kilogram will show up there. It's a molecular weight type of quantity, molecular viscosity. But if you divide it by rho, you'll get something called kinematic viscosity. It's got a units of meter squared over second or feet squared over second. Velocity times distance as a unit. Therefore, the kinematic viscosity has got a kinematic dimensions, nothing to do with mass. Therefore, it's called a kinematic viscosity. Molecular viscosity, kinematic viscosity. So we encourage you to verify these equations and make sure you get these. So this concludes the derivation of two-dimensional Navier Stokes equations. We could similarly develop 3D Navier Stokes equations. We will go ahead and write it down at some future time.